This video is about Proton Nmr Spectrum. So we're going to read Proton Nmr Spectrum. Before this, you should already have some knowledge about organic chemistry. Okay, that said, Proton Nmr. So our main focus here is the hydrogens that attach to something. For example, ethanol here. So you do need to have some organic chemistry knowledge to do this part. Okay, let's view this ethanol as, let's see this carbon as a house. And this house is rented and shared by two occupants. We'll view the protons as the occupants in the house. Now let's relate this to the spectrum. Okay, so if you were to integrate and get the area under the peak, so you get the area here, area, by integration. The area under peak is the ratio of the occupants, meaning this peak represents one proton, this peak represents two protons, and this peak represents three protons. So these represent the occupants. Next, the peaks. If you count the peaks there, the peaklets, so I have a triplet there, example, a triplet here and a quartet here, so that's 4, right? So I call those peaklets, that smaller peaks there. The peaklets will represent, if you take the peaks minus 1, represents who are their neighbors. And each set of peaks represents a house. So this is one house, and this is another house. We'll talk about that singlet later. Now keep in mind, this is not carbon NMR, so it doesn't read the house, but it only reads the occupants because it's Proton NMR. So let's focus on the red carbon here. Read together with me. 2 occupants here, 2 occupants, has 3 neighbors. So 2 occupants has 3 neighbors. So pick, there's 4 picks here, minus 1 equals to 3. So 2 occupants has 3 neighbors. Let's focus on the green carbon this time. Read with me again. 3 occupants. These 3 occupants has 2 neighbors. And the 2 neighbors, it's a triplet here, so 3 minus 1, I will get the number of neighbors. The conclusion, the numbers up here are for the occupants, the ones that are living in the house, and the picklets represents neighbors plus 1. So if I bring the 1 over to the other side, I can say pick represents neighbor plus 1. Now, what happens to this singlet here? Okay, what does a singlet represent? A singlet can represent a few things. It could mean that this proton has no neighbors. So if no neighbors, 0 neighbor, plus 1, I will get a singlet. That is according to this picklet, minus 1 equals to neighbors. So if I have 0 neighbor, I would have 1 singlet pick there. Okay, but a singlet can also represent a proton that's on an OH. It would also give you a singlet. Okay, how do I verify whether it's something that has no neighbor or is it really an OH? You can prove that it's an OH. If you take your sample out of the NMR instrument and you shake that with D2O, say shake the solution with D2O. What's D2O? D2O is a heavy H2O. It's the isotope of hydrogen. Okay, if we shake that with D2O and then we put it back into the instrument and run the spectrum again, you will get another spectrum whereby that singlet disappeared. So you'll still see the quartet and the triplet, but there's no singlet here. It disappeared because it has become CH3, CH2, OD, and this instrument can only read a proton, a H. So it doesn't read the isotope of hydrogen, deuterium. It doesn't read a D. So if it has become CH3, CH2, OD instead of OH, that peak would have disappeared. Then you can verify that, oh, it's an OH and not a proton that has no neighbors. The same thing would happen if you have a suspected NH. So only these type of protons on an O or an N, they can have this proton exchange and become a D there. So you get ND2 instead. So as you can see, those in OH, those protons that on this OH, we don't look at the neighbor at all. It's not a normal house. It's not a carbon. So we don't look at it as one of the house. Keep in mind that this H-NMR spectrum, they are reading the proton environments. So if two houses have the same environment, it will read that as one set of peak. So you will not get a separate set of peak if there's two houses, they have the same number of occupants, and they feel the exact same environment. Okay, how is that? If I have a structure like this, let's imagine this as, say, a playground or something. So these three occupants has no neighbors, and these three occupants also had no neighbors. They are the same distance from the playground, so they have got the same environment. In that case, you're only going to get a singlet for all 6 protons. So this is when they're symmetrical. You get a clue that it's symmetrical when you get numbers like 6 or 4, because if you have 4, it's impossible to have 4 hydrogens in one carbon and there's still some other thing going on. That would be 5 bonds, which is impossible. And 6, you can't have 6 protons on a carbon, so that is also not possible. So you get a clue when the proton the occupants is more than 3. Another symmetry example, okay, I'm not going to focus on the OH, but I'll focus on what's on this tetrahedral shape, CH3, CH3, and CH3. Again, I treat this as like a playground. These 3 occupants have no neighbors, no neighbors, no neighbors, and they are the same distance from the playground. They all feel the same environment. You might get 9 like this, and 1 more for the OH. This is for the OH. So you get 2 sets of pick. This is one environment, and this is another environment. Okay, more examples. Next symmetry example, what might I see for this ketone here? So 1, 2, 3, 4, 5, 6 of them have the same environment. They'll all fall under one peak, but it's for 6 of them. How many neighbors do each of them have? They've got 2 neighbors. So in this neighborhood, 6 occupants has 2 neighbors. So neighbor plus 1 will be the peaklet. I'll have a triplet for 6 of them. Because all 6 of them, what do they feel? They have 2 neighbors. What about the other 4? The other 4, they're also the same distance to the playground, and they've all got 3 neighbors. So 3 neighbors means 1, 2, 3, 4, a quartet. How many of them has 3 neighbors in this neighborhood? 4 of them. You might get a ratio of 2 to 3, but it represents 4 to 6. Next, a benzene ring. If you have the H here, they are not much difference. Of course, the environment is a little bit different, but not a lot of difference. They all feel almost the same thing. You can see clearer how different are they in a carbon NMR, which we're not covering in this video. So for H-NMR, you will probably see a singlet for all 5 of them, or you might see a messy peak for that 5 of them. And this will give you another peak for no neighbors. Next, we're coming back to this picture here. What's on the x-axis? That is the chemical shift. The chemical shift is in ppm, parts per million. And you can get this reading. We will use it later, not just yet. You can get that reading from the data booklet. If you're doing the IBDP, it's here. And if you're doing A levels, it's also here. Our next discussion is about TMS. What is TMS? Tetramethylsilane. What's this tetramethylsilane? It's 4 methyls, silicon like that. And this is assigned as the 0 peak for all our reference, whether you're doing IBDP or A levels, or if you're going to use that in university, we always use TMS as our reference peak. That will be 0 in our spectrum. Okay, why do we use TMS? The first reason is because it gives us a very strong signal because of that 12 hydrogens or 12 protons here. We rather call them protons. So 12 protons here have the same environment. They're all next to this silicon. So that gives us a very strong signal. That is one reason. The second reason is because the chemical shift is low, comparatively low compared to other organic compounds. So if we have something like ethanol just now, the chemical shift of TMS will not disrupt any of the chemical shifts here. So it has low value of chemical shift. So it does not interfere with the peaks that we are interested in. And the other reason would be because it's not toxic. And also it's inert, doesn't react with your organic compounds. Okay, so now we're all set to determine the structure when we're given a spectrum. Okay, so this is C3H6O. So all the protons are in the same environment. How am I going to draw this? Let's put this in a table so that we can clear our mind. I'm going to put the picklets, just singlet. And it's somewhere, I don't know, 2.3 maybe. And suggested structure, I need all 6 to be in the same environment. I told you before, I can't put 1, 2, 3, 4, 5, 6 on the same carbon. So they can't all go into the same house. It's probably 2 houses with 3 each. So another one. Okay, I'm going to circle the occupants so that I do not get it mixed up with the neighbors. They should all have no neighbors because it's a singlet here. So these 6 should have no neighbors. I've already drawn all my 6 H. I've drawn 2 of the carbons. I have 1 more carbon left. And I have an oxygen here. So let's draw this CH3 and another CH3. What do I have left? Another O. Do make sure that all your carbons have 4 bonds, your hydrogen have 1 bond, your O have 2 bonds, and your N have 3 bonds, the basic organic chemistry knowledge. Next example looks like it's an isomer of what we had before this. Okay, but there's 3 sets of peak, meaning 3 different environments for these 6 protons. Okay, there's a 9.7 here, which gives me a big clue. We'll start using the chemical shift now. Okay, let's start with the peaklet. So a triplet there, which is 9.7. And this is 1, 2, 3, 4, 5 quintet. I'm going to show you how to determine more clearly, how do I know this is a quintet and why don't I count this as a sextet? Okay, later after this. This would be around 2.4, so plus minus. And there is one more triplet, around 1.0. Now these have 1 oxygen, so I can already suspect it's an aldehyde or a ketone. Probably not an alcohol because it's 3 and 6 here. But of course, if it's a very complicated question, it could be a double bonded alcohol. So it's possible, but I would suspect aldehyde or ketone first. Let's look at the data booklet. For an aldehyde, do I have a high number for chemical shift? I do. So for a H that is beside the CO, this is an aldehyde, CHO. It gives me very high figures. Okay, this is for IB, and for A levels, aldehyde, the H that's on the CO and an aldehyde gives me a very high figure. So I would think this is the aldehyde. So suggested structure, I'm going to put the COH here. I'll circle that, not to mix it up with the neighbors. So since it's a triplet, 3 minus 1, it has 2 neighbors. I'm not going to circle the neighbors, so we won't get mixed up. So this set of peak is for this proton here. Next, I need to figure out the other 5 protons. This has a quintet here. So it would have 4 neighbors. How am I going to draw 4 neighbors? So a hydrogen, a proton that has 4 neighbors. It could be left and right. It can't be all on one side because it can't have 4 hydrogens all on one side. So this is not possible. Okay, another option would be a proton whereby the right side, it has 1 neighbor and 3 neighbor on the other side. We'll decide which one is valid later. Next is a triplet. So this proton, triplet means 2 neighbors. Okay, so I have broken pieces like this and I need to overlap them. Let me just draw the confirmed structure first. So for sure I have this. I have this. Now, which can this be? I would think 2, whereby next to it there is 1 and 2, 3, 4 here. This H must have been this H. That is my guess. And the last one, this one, is probably one of these who has 2 neighbors, which are these 2. So let's overlap all 3 structures. So that red color proton must have been these protons. They've got 1, 2, 3, 4 neighbors, 1, 2, 3, 4 neighbors, and this green colored proton must have been these 3 green colored protons because they must have 2 neighbors and these green protons have 2 neighbors. Okay, why didn't I choose the other one? This one could not overlap this. This proton has 2 neighbors on the left and 2 neighbors on the right, but this can only have 1 proton neighbor here, and there's only 3 carbons. So there's nowhere to put this structure. So I did not choose this structure, I choose I chose this one because it fits into my puzzle. Let's try another one. Quartet. Like this. Singlet. This and triplet. And the figures say 2.5. This singlet maybe 2.1 and 1.1 maybe. Okay, let's do the same. Someone has 3 neighbors. Someone has 3 neighbors. Someone has no neighbors. No neighbors could also be just one side. And someone has 2 neighbors. Let's also use the chemical shift, something that is beside a CO. This proton is beside a CO. It gives me around 2 to 2.5. Same here, you can look for it here. Something that is beside a CO. Beside a CO. Beside a CO. Okay, so this should be beside a CO. So I'm going to draw the CO there for that singlet. After you've done lots of NMR spectrum practices, you'll find that someone has 3 neighbors and someone have 2 neighbors. It's usually 2% has 3 neighbors and 3% have 2 neighbors, and they're actually CH3, CH2. So 2% has 3 neighbors and 3% have 2 neighbors. So this and this is probably stuck together as a CH3, CH2. I'm going to draw that. CH3, CH2. I'll put colors on that. So the yellow proton has 3 neighbors, and the green proton here has 2 neighbors. Okay, also keep in mind, this one should not have any more neighbors here because it only have 3 neighbors. It's a quartet, so I shouldn't put any protons on this next door carbon. And this is also at 2 point something, so it's probably beside the CO as well. It will be perfect if I put a CO there. Okay, now should I take the left or the right structure to overlap this? So I have a CO and H. Say this H, or is it this H? If it was this H, there would be another carbon here, which is not possible because there's only 4 carbons. So I'm going to choose this structure to overlap my puzzle. This is my red protons, which are these. And so these would have no neighbors, singlet. These would have 3 neighbors, quartet, and these would have 2 neighbors, triplet.